Alright, so this video is going to introduce you to Faraday's law. What we have right here is a light bulb, and you can see a coil, and it's visible the electrons that are supposed to be able to flow. And right now, we have some magnetic field strength going through the coil, but it's fairly weak. However, if I move the magnet through the coil, we see something happen. The light bulb turns on, and the electrons start to move, like there is a current moving through. But if I just put the magnet in between the coil, nothing happens. It's only when I move the magnet through that we get a current, and thus the light bulb turns on. So as we change the strength of the magnetic field through the coil, so we go from big to little, we see the electrons move and there's a current flowing, and so the light bulb turns on. If I leave the magnet in between and I go over here and adjust the size of the coil, so the area through which the magnetic field is present, it's not quite as a dramatic of effect, but you can see that the light bulb does turn on a little bit as I change the area of the coil. So talking about changes in magnetic field and area should sound familiar to you, because those are the components that make up the magnetic flux. So if we change the magnetic field strength, we get a current, and if we change the area the magnetic field is going through, we also get a current. And the key word here is change. In the previous section of this video, we learned that the current occurs in a loop even though there's no power supply if there is a change in the magnetic field strength or if there's a change in the area. Now, because of Ohm's law, we can sort of use current and EMF here interchangeably. So Faraday's law is typically written in terms of an EMF, even though current is more the visible action where you're looking at something like a simulation where you can see the electrons flow. So Faraday's law states that the induced, and we call it induced because it's not coming from a power supply, it's coming from us changing the magnetic field strength or the area of the loop. The induced EMF in a closed loop equals the negative of the time rate of change of the magnetic flux through the loop. So in equation form, it's going to look like this, where the EMF equals the negative, and I'm putting an N out here because you could have multiple loops, of the change with respect to time of the magnetic flux. So the key thing here is that there is a change. So you only get an induced EMF if there's a change in magnetic flux. So notice that the word change is in here. You need that change in order to get that induced EMF. If there's nothing changing, the magnetic flux remains constant and there is no induced EMF. Now remember that the magnetic flux is equal to the magnetic field strength times the area times the cosine of phi. And any of those variables changing can lead to an induced EMF. So how we write the change in magnetic flux depends upon what is actually changing in the system. If there's a change in the magnetic field strength, or if there's a change in the area of the loop, and you can also have a change in the orientation of the loop. So how you actually write the change in magnetic flux depends upon which variable is actually doing the changing. And this means that if you're given a function, so if you're given a function of magnetic field strength with respect to time, that means that once you plug in our formula here for the change in magnetic flux, you would then have to do a derivative in terms of time of that function for the magnetic field strength. So there could be some calculus involved in these problems. But it's incredibly important to remember that in order to get that induced EMF, there must be a change in one of those variables. If nothing is changing, there is no induced EMF.